Okay, like we're possibly live, and so what we're gonna do in this stream is talk about what we were doing yesterday, which is just the phenomenon, I think well known, although I've never really seen a paper directly discussing it, but like just the phenomenon if you have a pre-trained classifier, image classifier, you can start, you can create some images that are random noise, and then you can back propagate to these images, or yeah, to the pixels of the images, whilst trying to maximize one of the class's outputs from the image classifier. And that will actually work. So you will end up with these images that maximally activate, in this case, these images cause the classifier to classify them as analog clocks with 99.9% probability. And so we're just trying to understand perhaps what's happening, because that kind of seems weird. Yeah, right, because I mean the observation is that they, if you look at them as a human, they don't really resemble analog clocks in any way. I mean, you can kind of, I mean, if you stare at them long enough, you can say, you know, it's like, oh, this is kind of a circular thing. But, you know, I mean, it's, yeah. So anyway, that's kind of what we're trying to do, is try to understand, like, why are these images causing the classifier to classify them as analog clocks when, like, they're really not even natural images. And so yeah, let's yeah, I mean, I'm kind of assuming that I want to run pixel saliency to see what that does. So, like, from what I can tell, this method is the I guess current state of the art for, like, pixel saliency. I mean, I don't know, it could be wrong since it came out in 2019. But yeah, so like this is kind of what it does, or this, I guess. Yeah, like if we could get this thing happening on our fake images, I guess we're calling them, or, you know, like these images. Yeah, if we could get that happening, that may or may not be cool. I mean, like, we ended the last stream kind of doing a similar analysis using ablations and of the images. And so we were taking one of the images that is classified with high probability as a wall clock or an analog clock, and running a square across the image to determine the effect on the classification. And we found that some of the locations of the square ablation do cause pretty significant changes in both like the classification itself and sometimes the confidence of the classification. Which again is like, how do you even like interpret that? Like, because I mean, like what this is saying, like the first two situations, we have a complete change in the classification. It's like this is a wall clock, this is not a wall clock. So kind of implying, I guess, like there's something in this set of pixels right here that is necessary for the correct classification. Or like a subset of those pixels. Yeah, I mean, like it's kind of hard to interpret. So, yeah, we're gonna try to, yeah, like I don't know, try to develop some sort of like conceptual understanding. We also had these other observations from yesterday, which is if you randomly, like uniformly or Gaussianly, or like each pixel independently distributed either uniformly between -1 and 1 or Gaussianly between -1 and 1. Well, actually, just Gaussian centered at 0 with some sort of variance. Almost all, or literally all of those images are classified as velvet, like with 0.5 confidence. And I mean, we didn't do like a extreme, like we didn't test like a ton of images, but that kind of implies that the majority of the input space for mobilenet, which are these vectors that are 224 by 224 by 3, and they're all, I believe, in the range -1 and 1. So it's this hypercube. It's the volume of this hypercube and whatever dimensionality this space is. It's like this kind of gives like very weak evidence that the majority of that volume is classified as velvet, which is kind of weird. But you can also find images that, again, using like gradient descent to the pixels, where the highest confidence class is 0.002, which I guess implies that the mobilenet just doesn't think the image is anything. Which is kind of weird. I mean, I would have naively expected this to happen on a random image. Like if you just put in a random image, it seems like you should expect, like the highest confidence class to be very like low confidence. That's not what happens. Like if you put in a random image, it's velvet with like 0.5 confidence, which is relatively high. So, yeah, so I guess like we want to talk about those, like these fake images you know, that are any fake images. So, right, I mean, like that. I mean, I guess, like, okay, so it's like one, I guess, observation would be if, like, if you consider, like, a low-dimensional space, and your, you know, so, like, if you just consider, like, you know, if you consider, like, R3, you know, a unit cube in real numbers or something, although, like, real numbers do not exist. But anyway, if you consider R3 and then you consider, like, just like a hyperplane classifier, then you know, like, all the points in R3 will be classified, you know, even if the real, like the data points, I should say real space data, the real data points, you know, are tightly clustered in R3. So I think, like, I mean, like, if that's the case, then I guess, like, in some sense, it's not necessarily interesting that you can find, you know, fake images that have a particular classification, because, like, on, I mean, you know, I mean, on some level, a neural net is computing these hyperplanes. And, so, I mean, yeah, like, you have to classify all the points. But I mean, I guess, like, a counter to this observation, though, is the point from above, which is that the majority of the points are classified as velvet. Okay, let's like test that more statistically. But the majority of points are classified as velvet, probably. Okay, so let's just run a ton, I don't know, like 1,000 points and see what they're classified as. So, yeah. Yeah. So, okay, so I just need to, I don't need to train anything. So I'm just going to import the mobilenet and then set up an input batch. And I guess then, like, collect the frequency of you know, each class. So I'll just do that here. Okay, no. Okay, so this is going to be the input batch. It's going to be like uniform distributed. So we're uniformly sampling 1,000 points, if you can believe it. I should probably do like 10,000 or something, but it also turns out like it's very difficult to think about like high dimensional spaces or whatever. But okay, so this is like our batch, and then we're just gonna run the model on the batch. And like decode predictions. Yeah, so we'll do like a frequency thing. So from collections import counter, and then I forgot how to use a counter. Frequencies is, oh yeah, you don't do that, is a counter. And then I think you just say like freaks, like this. No. Is that how you do it? I forgot how you use a counter. 6 out of the last 9 calls to make predict function. Oh yeah, I could see that. Fair enough. Yeah, you should just call that once. That's why it keeps complaining. Yeah. I think you... Do you do it like this? Or... Actually, we have all the predictions, so I think you can just throw it directly into the constructor. So we need decoded I1, like, oh no, it's I01. So that'll just be a string, and then just print Now I'm not using a GPU, so this might be slow. Yeah, like we're in the predict call. Okay, now we're in cell. I'm not entirely sure what that means. Delete iterator. Oh yeah, I forgot to do that. Okay, let's just say D or D and decoded, and I'm gonna do that on a separate cell so it doesn't rerun. Actually, I'll just turn that. Okay. Too many values to unpack. Fair enough. Velvet 998 bubble 2.
Right? I mean, that's like pretty good statistical evidence that the majority of the volume of the input space of mobilenet is classified as velvet. Which, yeah. I mean, to me, kind of implies that, like, the fake images, like, are interesting somehow. Right? Like, it's not just you have, you know, like a big hyperplane. So yeah, I think we'll try to implement this. We're gonna try to implement this, and it's kind of weird because we're generating images using gradients, and then like we're analyzing the images using gradients. I'm not entirely sure that's like sensical, but I think that makes sense. So yeah, we'll see if I mean, it's possible. I mean, probably unlikely, but it's possible that, you know, there is some subset of pixels in our fake images that look like clocks or whatever. So I guess we'll test that hypothesis. So, okay, so we're going to implement this, and which is a little annoying. So we want guided grad cam. So the grad cam itself, from what I understand, is they just take the last layer, I think the last convolutional layer, and then they compute the, like, right, so like the last layer is like a stack of images effectively. And so I think for each pixel in that stack of images, like they compute, I think the gradient of, they compute for each pixel, like if you increase the intensity of that pixel. So like you fix a class, and then you say like, okay, each of these pixels in the last layer, if I if I increase the intensity of that pixel, does that increase or decrease the classification? They also do the gradient, I think, before the softmax. So yeah, I think that's what they do, right? Let's see if I can confirm that. Okay, so first they do grad cam, which is this, and then guided grad cam, like, gives you like high resolution, I guess, pixels, because grad cam is actually computed in the resolution of the last layer, which like isn't necessarily the pixel resolution. So GradCam. These are the heat maps. So GradCam convolutional layers. The neurons in the last layer look for semantic class-specific information. Does it though? GradCam uses the gradient information flowing into the last convolutional layer of the convolutional neural net to assign importance values to each neuron for a particular decision of interest. We focus on explaining up. Okay, so in order to obtain the class discriminative localization map, LC GradCam of width U and height V for any class C, we first compute the gradient of the score for class C before the softmax with respect to feature map activations AK of a convolutional layer. Right? These gradients flowing back are global average pooled over the width and height dimensions to obtain the neuron importance weights, alpha CK. What is Z? I don't know, Z. Why would they do that though? Because K, the neuron importance weights, like K is the layer. So like they're collapsing the entire layer? Computing alpha KC while backpropagating gradients with respect to activations. The exact computation amounts to successive matrix products of the weight matrices in the gradient with respect to activation functions till the final convolutional layer that the gradients are being propagated to. Hence, alpha KC represents a partial linearization of the deep network downstream from A and captures the importance of feature map K for a target class C. We perform a weighted combination of forward activation maps so feature map K, so for each feature map, so you're summing over all the feature maps in the last layer. You're computing this alpha KC, which is like the average gradient in that feature map. And so you're just taking the linear combination and then you're taking the ReLU. Okay, let's do that. So implementing, what's it called? GradCam something? GradCam? Sure. Okay, implementing GradCam. Poorly. We're implementing it poorly. Okay, so what do I call the model? Because like I need to get the layers, which is going to be a pain. Okay, model layers. Let me have them. Holy, that is so many layers. Okay, so I think we want to look at this layer. Global average pooling dense. Yeah. I think we want to look at that layer, so that's like 3 back. So, and outputs? Oh no, has no attribute outputs. Okay, it's 7 by 7 by 1280. I feel like that's gonna be weird. 7 by 7. That seems like way too small. Can I show that? I mean, like, does that just retain like the last state? No. It does not. Okay, so I need a layer is tf keras model inputs equals model dot inputs outputs equals model dot output. And okay, now let's run layer. What did I call the okay, I'll just create a new, okay, tf dot random uniform, and it needs to be one batch of 1, 224, 224, 3, and from like -1 to +1. Hello. Look at that. That is very cool. And so we'll visualize some of them just to see what's happening. Because keep in mind, there's like a 99.8% probability from our earlier statistical analysis that this is being classified by the net as velvet. Which kind of makes sense because, like, I mean, I guess velvet is like a weird, I mean, it's just like a texture. So, like, I think basically anything could be velvet. So, what am I doing? Oh, yeah, okay, I was going to visualize these. Just some of them, though. Yeah. Okay. Visualize. See, I don't see how you're going to go from 7 by 7 to 224 by 224. Like, that seems to be the problem thus far. Yeah, we'll look at 25 of them. That's fine. So we want to look at the output. I guess it needs to be numpy and output 0 RC. I think that's all you need to really say. Oh no. Why doesn't it like it? Where's the error message? Oh. Oh, right. Oh, no. Yeah. All of that, the width and the height, and then it's this one. R times 5 plus C. Okay. Oh my god. Neat. Wow, that's cool. Okay, let's like look at some more, you know? Let's look at 100 of them. That's probably too much. Okay, bombs away. Right. Also, let's compare this to one of the images that look like a clock, right? A little diversion here. But also, let's look at even more. Also, I need to turn off the axes. And I don't know how to do that. It's like dot X axis display. This is not gonna work. Equals false. Did that work? Holy wow. Oh no, it didn't work. Okay, so what am I doing? Matplotlib turn off like axis, whatever. For subplots. This isn't how I usually do it. Great. You just say axis off? Okay, we'll try that out. Internet. When you say axis off, jeez. So this is why you need GPT-3, you know? Whoa. That is very cool. So this is 400 images. So it's like, they all just seem to be big blotchy images. I mean, or they're off. Okay, so let's get a image that, this is kind of a sidetrack, but we're going to get a fake image that is classified as an analog clock, even though it does not look like an analog clock. This is the error of the current classification. It is dropping. So like the grad cam thing though, from what I understand, is like you're gonna look at all of these, and for each feature map, like each of these is a feature map, you are going to compute the gradient, okay, for each pixel with respect to the class before the softmax. Although it didn't look like mobilenet has a softmax. So, so you compute all of those gradients and then you average over all the pixels within the feature map, and then that gives you like an alpha KC or something. And then you take these activations, you weight them by the alpha KC, and then you sum them all together. And then like that gives you, somehow that gives you like a localization. I'm thinking, I mean this, I mean it doesn't seem like this is going to work because like these are 7x7 images and like the pixels are 224 by 224. So that doesn't seem like it's going to work. But anyways, okay, so we found like these images, and let's just for confirmation run them through the mobile net. They're all 99.869% probability that it's an analog clock. And then if you don't think it's an analog clock, it's like a wall clock, and then it's a sundial or a stopwatch, right? I mean, it's clearly in the circular object with straight lines category. Okay, so let's just run. So, okay, so we're going to compare the last layer activations, or like the last convolutional layer activations with random uniform. So these are random uniform. Okay, let's all memorize that. Good. And so we're gonna say now the output is layer, and yeah, that's fine. Okay. Okay, so let's all memorize this. Good. It's blotchy, kind of. I mean, you have weird shapes, you know, like triangles and stuff. All right, let's do this one. Yeah. I didn't really get anything out of that. I mean, they look the same, basically. Now, if I had an actual picture of a wall, what is it, an analog clock? Yeah. I guess I could do, yeah, alright, let's do that. Let's get an actual picture of an analog clock. That's annoying. No, I don't need this. Okay. Yeah, I'll do it in a separate cell. Okay. So, alright, so I need to go get an image of a clock off of the internet, and I don't know how easy that will be to do. Yes. All of this. So I just need this and all of that. Copy paste down there. See, like if I had a GPT-3, like you don't have to do this. You just put it in natural language and then you're cool. Okay, so that, and then the other stuff I needed, which was this. Yes. Okay. That one. Do that. And, so we now have to go out on the internet to find a wall clock. Get a, wait, what is, no, analog clock. Get a analog clock picture. Alright, that shouldn't be too hard, you know. Okay, just go over to Google. I'm just gonna type in analog clock. Oh my god, it worked. Yeah, that one's fine. Can I get the URL? I guess not. Yeah, I mean, any of these is fine. Can I just... This one has Wi-Fi, so that's cool. Okay, I need the URL for the image. Inspect. And that's it. Okay. Copy link address. Very cool. And then copy and paste. Okay. So this should show the last layer activations for an actual analog clock. Although we should actually, you know, check that it actually classifies it as an analog clock. I'm gonna call it actual clock, and then we're gonna pass actual clock. Okay, this should totally work. Oh no. Image file. Cannot identify image file. Well, I don't see why not. Oh my god. It just says .raw. Alright, we'll try one more then. I will completely abandon this because this is a waste of time. I don't see why that doesn't work though. Print rec. I'll just try a different one. Oh, it works now. Weird. So what is it doing? Oh, it's whoa. Okay. Okay, so like this is 400 feature maps from the last convolutional layer for an actual analog clock, which we're assuming is correctly categorized as a, yeah, I should also check that. I already forgot how to do that. Yeah, I just want this for the image. So let's make sure it is classified as a clock. So we want to predict from actual clock. I don't know if it'll take that directly, but we'll find out. And there's only one prediction. Hey, oh, it's only 77% sure that it's an analog clock. Right? So like our fake images are 99% sure. Okay, but so this is the real image where it's 77% sure. And this is the fake image where it is. Also, I'm wondering about the scaling of the colors. I mean, definitely like the fake image has more activity, it looks like. Yeah, I mean, like it's... But I mean... Okay, let's get another image. Well, alright. There's two things. One, I'm worried about the scaling. Is this a ReLU? See, like, I don't know the value of... I'm just gonna guess, like, -2 and +2. And then we're gonna do that for the other one as well. So that way we can, like, be looking at the same color scale. Oh, okay. Are they all positive outputs? I don't know. Anyway, okay, this is the fake. This is the fake images. I mean, it's definitely more activity. Okay, and then let me do one more for like a different class, but like a real image. Just to see what that looks like. I mean, they don't really look like anything, but... Okay, so I need one more for a different class. I'll do hen, because that is what I was doing previously. Is that a hen? Sure. Looks like a hen to me. I'm going to steal your hen. Alright, so get a hen picture. And, yeah. Oh, I overwrote actual clock. Whoops. Okay, so this is a hen. It does look different, actually. It's like a different shape. I mean, that just looks like a small hen. And that looks like a small hen. So, like, if you look at these, this is for the hen. This is for the real clock. Yeah, like, those aren't even activated over here, from what I can tell. And on the fake one, those also aren't really activated. Okay. Anyway, so... okay, yeah, so we want to try to get GradCam working. Like, I just spent the past 20 minutes not doing that at all. Okay, so we have the last layer, and this is the last layer, and we want to compute the gradients of the last layer with respect to the class before softmax. And I don't think the model has a softmax, from what I can tell. Yeah, it just has a dense. So I guess we don't have to worry about softmax. So we need to, I think, just do something like okay, so we define the model, and so we're like, also this is a hen, actual hen. Okay, so we need to say with TF gradient tape as tape, like compute the output, and then the gradients are just tape dot gradient output gradient. So the gradient of, I think we need a 1-hot for the hen class with respect to the layer dot outputs. And then that should directly just give what we're looking for. But I need a 1-hot for the hen class. Which first of all means I need the 1-hot thingy. Where was I? Yeah, okay. That's TF 1-hot. And I don't think I need this stuff because I think that's like default. And so I'm just going to put on one line. Okay, so then I just need to know what the hen number is. Which means I'm going to Google. So what are we doing? ImageNet. Is it ImageNet? Yeah. Labels. Yeah. I think it's 7, actually. Nope, it's 8. See, I'm glad I checked. Alright, so that just needs to be like that, I guess. Alright, let's see. Oh no. Keras tensor object has no attribute ID. Yeah, I think you just want to say output. That'd make more sense. Maybe. None type object has no attribute. Okay. Output dot outputs. Oh no. What about output dot output? God damn it. It's an eager tensor. Do I need to say predict? I don't think that is what the problem is, but we'll try that. Oh, God. No gradient defined.
Well, this is not going well.
Actual hand dot shape. Yeah, I mean that's the right shape. So you throw it into the layer and it doesn't like it. Okay, now it likes it. And where is this coming from? Oh, that's the output shape, right? TF. No, it's... output. Yeah, I mean, that doesn't actually make sense. We're taking the gradient of a vector. I mean, well, no, I mean, all you want is the 8th input to increase. So yeah, this might not even work because it's like... Okay, let's say layer output. There's gotta be like a better way of doing this, but whatever. We want to compute. See, I don't think it can necessarily do this because I don't know if layer output is a variable, and I don't know if you need to compute. Like, I don't know if that has to be a variable. It might be a variable. I don't know. Yeah. Okay. So then the actual model output just minus. Yeah, like the target output. Okay, and then go back to the training thing from above where it worked. Yeah. Target class. That's what we're doing. Oh no, I lost my spot. So we want the difference between target output and the model output. Hopefully this works. No. Oh, it did work. Wait, did it? No, it didn't. It didn't. Like, what is layer output though? That's a tensor. Does it have to be a variable? Like, yeah, this isn't, no, I think I need a new model. I'm gonna have to think about this. This turned out to be harder than I thought.